Hello everyone, my name is Aditya Tiwari, Assistant Professor, CSVTU Bhilai. In this tutorial, we cover AVL tree. So before we are starting the AVL tree, we have to understand the drawback of binary search tree. In the previous tutorial, we already discussed about the binary search tree. In a binary search tree, comes in a sorted way. Sorted means if your data elements are either in the ascending order or in descending order manner. In that way, you adjust your data in a either in ascending way, either in a descending way. Suppose you generate a tree by the elements which are on the sorted way, either in ascending order or either in descending order. So you generating the tree, so all elements are fixed in a one way order, like that. Suppose you when you are talking about the ascending order, so first element it will be a shortest element, then all the elements are the bigger than as compared to the root node elements, and definitely they will fix at the right subtree of that particular node, like that 10, like 14, like 19, like all our item are shifted to the right hand side of that particular tree. Suppose the data item are in the you fixed in the descending order, the biggest item will be a root node and all the smallest item taking only the left position of that tree. So that tree is not a balanced tree. If you balance tree, it means when you are searching an element and that tree is a one way tree, it is a kind of a linked list, that kind of a linked list. It means you are performing a searching operation in a one way only. It take a same time to search that elements like as in the one way sequence tree. So it is not a comfortable, or it's a time taken process which we are using in a binary search tree. So for this manner, this is a drawback of binary search tree. It will take us some time. So we convert this binary search tree into the balanced tree. That balanced tree name is the AVL tree. So it is observed that binary search tree a worst case performance in closest to linear search algorithms. That is O of n. N is the number of elements which are occupied in the tree. In a real time data, we cannot predict the data pattern and their frequency. So a need arises to balance out the existing binary search tree, named after their inventor Adelson, Walensky and Landis. The name of the three persons, the inventor of this algorithm, that is Adelson, Walensky and Landis. Then by the name of that one we can call the AVL tree, our highest balancing binary search tree. AVL tree checks the height of the left and the right subtree as compared to the root node, left and right subtree, and assures that the differences is not more than the 1. This difference is called the balancing factor, or we can say balance factor. So the definition of AVL tree is that AVL tree is the highest balanced binary search tree. That means an AVL tree is also a binary search tree, but it is a balanced tree. A binary tree is said to be a balanced if the difference between the height of the left and the right subtree of every node, of each and every node in the tree is either -1, 0 and +1. In other words, a binary tree is said to be a balanced if the height of the left and the right children of every node means I am talking about the root node, all the internal nodes. Each and every nodes differ by either a balancing factor -1, 0 or +1. I will discuss you in the next slide how we calculate this all the balancing factor -1, 0 and +1. In an AVL tree, every node maintain an extra information known as balance factor. This is a range, the -1, 0 to +1, this comes under the balancing factor. So by this example we can understand how we calculate the balancing factor, or how we calculate the balancing range. So in our first part, in our first tree, Here we having items, B is a root node, A is a left child of B, and C is a right child of B. So we calculate the balancing factor of leaf node. Like leaf node, as I told you, which do not produce any child, that is called a leaf node. Here we having A and C, both are the leaf nodes. So first we calculate the balancing factor of A. So A is a leaf node, it means no left child, no right child. It means height of left is 0 and the height of right is also a 0. So 0 minus 0, that is comes a 0. That is why the balancing factor of A is 0. Same C, height, again C is a leaf node, it means no left child, no right child. It means height of left child is 0 and height of right child is again 0. So 0 minus 0 is again comes the balancing factor of C is 0. Now talking about the B, B is a root node of that tree. So height of left node and height of right node. Height of left having only a single path, that is a single path. It means the height of left is 1, and talking about the right one, only a single one path is available, that is C, B to C. The height of the right path is only a 1. So height of R is 1 and height of left is also a 1. So 1 minus 1 is again a 0. So the balancing factor is 0, 0 of B. So all the nodes having a balancing factor are 0. That comes under the range. That's why we can say this tree is a balanced tree. Now we are talking about this second graph. Here we see we are having again 3 items A, B, C, but right now C is a root node of that tree and there is no any right child of that tree, but having a left child, that is called a B. B is a current successor of C and B also having a child, that is a A. A is a current left successor of B. Here you check B, there is no any right child. C, there is no any right child. A is a leaf node, there is no left child and no right child. So we calculate the balancing factor of A. So A is a leaf node, so height of left child minus height of right child is again 0. Now talking about the B. B having only one left path, left successor, and having only one left child. That's why height of left is 1, and there is no any right path, right child of B. That's why the height of right child is 0. So height of left minus height of right one, the 1 minus 0. So the balancing factor of B is 1. Now we calculate the topmost one, that is a root node, that is a C. So height of left one is first path is C to B and second path is B to A. Already in the previous one we already discussed how we calculate the height. So that one first is 1 up to B, then up to A is the second one. The height of left child is 2 and the height of right child of C, particular right child of C, there is no any path, there is no any edges from C to the right hand side. That's why the height of left child is 2 and the height of right child is 0. 2 minus 0, so the balancing factor of C is 2. So this tree is not balanced because this exceed the range of the AVL tree, the property of AVL tree. As I told you, the property of AVL tree, the range is 0, 1 and minus 1, not bound that the minus 1 or 1. So here the balancing factor is 2, it means not satisfy the property or rule of AVL tree. In the same manner, in a vice versa, the mirror image in the third slide. Again A is a root node and B is a current right successor of that A, and again C is a current right successor of B. There is no any left child of A, no any left child of B, and C is a leaf node. So first we calculate the leaf node, balancing factor of leaf node. Here we are having only a single leaf node, that is called as C. So the balancing factor of C is height of left minus height of right. There is no any item is available because C is leaf node, that's why the balancing factor of C is 0. When we calculate the B1, so height of left is again there is no, B is the internal node, but only having a one child as a right child, no any left child. So height of left child is 0, but height of right child is 1. That's why the balancing factor of this one is 0 minus 1, it means minus 1. And the last one, the root node is A. So, height of left child is, again there is no any left child in the left hand side, but having a right child, talking about the right child, there is a 2 generations, one is B and one is C. So, height of right side is 2, height of left child is 0 and a height of right child is again 2, 0 minus 2, it means minus 2. So, we can use a mode also for that one, if we putting the mode inside the operation. So, we can write 2 also, or if we do not put the mode functions, we can write 2 also. As you know, the property of mode, whatever the value is negative, it will be a positive, as you know that the functioning of mode. So, again in the third graph, you can see the balancing factor of C is satisfying, B is also satisfying, but the A is not satisfying, is exceed the range of that 0, 1, 2 plus 1, 0, 1 and minus 1, and the balancing factor of A is 2, so not satisfying the property of AVL tree, it means the tree is not balanced. So, for converting this, we having do the following operation to converting this unbalanced tree to not balanced tree to balanced tree. So, as we discussed already, so again I tell you how we convert in a second tree. In a second tree, the left subtree of C has a height 2 and the right subtree has a height is 0. So, the difference is 0. And the third one in the same manner. So, balancing factor of a node is the difference between the heights of the left and the right subtrees of the node. The balancing factor of a node is calculated either height of left subtree minus height of right subtree. So, the height of right subtree minus height of left subtree. In this following explanation, we can calculate by the follows. So, the balancing factor is equals to height of left subtree minus height of right subtree. Of its 2 child subtrees, a binary tree is defined to be an AVL tree if the invariant. So, balancing factor of any node in a tree is equals to range of that node is range of that balancing factor is minus 1, 0 and plus 1. Holds for every node n in the tree. You can calculate all the balancing factor of all the node which are available inside the tree. A node n with balancing factor is less than 0 is called left heavy. One with balancing factor is less than 0 is called a right heavy, and one with balancing factor is equals to 0 is sometimes simply called balanced. If the difference in the height of left and right subtree is more than 1, the tree is balanced using some rotation technique. So, we go for the rotation operation to convert a unbalanced tree to the balanced tree. By this example, we can calculate, first we understand how we calculate the balancing factor, then we go for the how we go for the rotation part. So, this is a tree, 25 is a root node and all the internal nodes are available, and we also having a leaf node also, that is a 12, 28, 38 and 48. So, first we calculate the balancing factor of all the leaf node, either a left hand side or either a right hand side. So, in the left hand side we having only a single, we having a 2 leaf nodes. First one is a 12 when you compare it with the 25. So, first leaf node is 12, it is a right child of 10. So, the balancing factor of 12 is 0 because there is no any left child, there is no any right child of 12. That is why height of left minus height of right both are 0, 0 minus 0 is 0. When you go for the calculate the balancing factor of 10. So, 10 again having no any left child, but having only single right path, right edge at the right hand side. So, we calculate the balancing factor of 10 is height of left child is 0, but height of right child is 1. So, 0 minus 1. So, the balancing factor of 10 is minus 1. Another leaf node is 22. So, we calculate the balancing factor, as the 22 is the leaf node, so balancing factor of 22 is 0. Now, we go for the 20. 20 is a parent node of 10 as well as the 22 and also is a grandparent of 12 also. So, we calculate the balancing factor of 20. Height of left minus height of right. Height of left having a 2 generations, first is 10 and second generation is 12. So, height of left is 2 and the height of right is only a single generation, that is called a right successor 22. So, we put the value only 1. So, height of left is 2 and height of right is 1. So, 2 minus 1 it means 1, again satisfy the property of AVL tree. So, balancing factor of 20 is 1, it follow the property of balancing factor. If you cross check 10 in a node 10 balancing factor is minus 1, but in a node 20 balancing factor is 1, both are comes under the range of AVL tree, that will satisfy the property of AVL tree. In the same manner, in a right hand child, first we calculate the balancing factor of all the leaf node, that is 28, 38 and 48. So, the leaf node are having balancing factor are common like 0, 0 and 0. Now, go for the internal nodes, that is called a 30, 30 is a current current parent of 28. So, we calculate the balancing factor of 30, that is a at the left hand side only a single path and at the right hand side there is no path, that is why height of left child is 1 and height of right child is 0. So, 1 minus 0, that is the balancing factor of 30 is 1. Again the balancing factor of 30 is 1 is a follow the property of satisfy the property of AVL tree or balancing factor. So, we can say this is a balance. Now, we calculate the another balancing factor of internal node of 40. So, 40 having only a sum 1 at the left hand side and on the 1 at the right hand side. So, only one edge is at the left at the right hand side. So, calculate the balancing factor height of left minus height of right, it means 1 minus 1. So, the balancing factor of 40 is 0 by the operation of 1 minus 1. So, again it comes under the range of balancing factor, that is why the tree is AVL tree. Now, we calculate the balancing factor of 36, that is again a internal node, but it is a parent of 30 and 40 and a grandparent of 28, 38 and 48. So, again we calculate the balancing factor of 36, height of left child, do not go for the count of nodes, you only count the number of generations. So, at the left hand side we having a 2 generations, first is 30, second is 28. So, the height of left child is 2 and height of right child of 36 is first is 40 first generation and second generation is 30 and 48 are the siblings, the both are in the follow the same generations, that is why height of right child is also a 2, height of left child of 36 is 2 and height of right child is also a 2. So, 2 minus 2 is also it comes under 0 and it is follow the property of AVL tree, because the balancing 0 is comes under the balancing factor. Now, finally, we calculate the balancing factor of all the root node of that tree, it means the parent of 20 and 36. Now, we calculate the balancing factor height of left child of 25 and minus height of right child of 25. So, at the left hand side how many generations? The first one is 20, the first generation, second generation is 20 and 22, 10 and 22, both are the siblings of 20, both are the siblings and both are the children of 20, that is second generation, and the 12 is the last third generation. That is why the height of the left hand child of 25 is 3. First is 20, second is 10 and 22, then third is 12. So, height of left hand side is 3. Now, height of right hand side child of 25 is first is 36, that is the first generation, then second generation is 30 and 40 are the siblings and the third generation is 28, 38 and 48 all are the siblings. So, it means there are 3 generation at the right hand side. So, at the left hand side is 3 and the right hand side is also a 3, that is why 3 minus 3 is a 0. So, balancing factor of 25 is 0, which comes under the range, that is why the complete tree is a AVL tree, because each and every node we are having a lots of node in this tree, but all the balancing factor of each and every node will satisfy the property of AVL tree, because the range of that AVL tree is comes under the 0, 1 and minus 1. So, we can say this tree is called a AVL tree, or we can say the balanced tree. The tree is a binary search tree and every node is a satisfying balancing factor condition. So, this tree is said to be an AVL tree. So, now go for the if tree is not balanced. If tree is not balanced, so we follow the property of rotations. So, talking about the rotations of AVL. In AVL tree, after performing the operation like insertion and deletion, we need to check the balance factor of every node in the tree. If every node satisfy the balance factor conditions, then we conclude the operations, otherwise we must make it balanced. Whenever the tree becomes imbalanced due to any operation, we use rotation operations to make the tree balanced. Now, we are talking about the rotation part of AVL tree. So, basically rotations are divided into two parts. First is a single rotation and second one is a double rotation. Single rotation again divided into two parts, that is a left rotation, or we can say LL rotations. Another example of single rotation is right rotation, that is called the RR rotation. We can write RR of first one is a left rotation, second one is a right rotation. This both are the part of the single rotation. Another property of rotation is a double rotations. Double rotation also divided into two parts, left right rotation, we can say LR rotation, and last one is a right left rotation, we can write RL rotation. These are the basically a four kind of technique to performing when the tree is unbalanced or imbalanced. By this rotation we can shift to the balanced tree. LL rotation, RR rotation, LR rotation and RL rotation. LN and RR comes in the single rotation and LR and RLR comes in the double rotation. We can see one by one how we rotate our tree by this rotation part. So, to balance itself, an AVL tree may perform the following four kind of operation as I told you. The first two rotations are single rotation and the next two rotations are the double rotation. Single left rotation, that is called a LL rotation. In LL rotation, every node moves one position to left from the current position. To understand LL rotation, let us consider the following insertion operation and AVL tree, or by this example we can understand how we perform a rotation part. So, in our first example, this is a question. In a graph we can see the 1, 2, 3 having a nodes, and we can calculate the balancing factor of all the nodes. First we calculate the balancing factor of leaf node, that is 3. So, leaf node balance factor is 0. Now, we calculate the balancing factor of 2. So, 2 they do not have any left child, but it have one right child. So, we calculate the height of left minus height of right. So, the balancing factor of 2 is minus 1. Now, minus 1 is comes under the range. So, it satisfies the property of AVL tree. But talking about the root node, that is called 1. So, calculate the balancing factor of that root node 1. So, height of left child is 0, but height of right child is 2, because the two generation are there. So, it means height of left child is 0, height of right child is 2, 0 minus 2, it means minus 2 is a balancing factor of 1. So, it not comes under the range of balancing tree or not the follow the property of AVL tree. So, we have to provide us some kind of a rotation operation. So, by this sign you can understand how which kind of operation we can perform. Here in a root node does not satisfy the property of AVL tree. So, here we check the sign of that one. Here we are having a sign is negative. It means by the negative sign you can understand the weight at the right hand side will be higher as compared to the left hand side. If the sign is positive, it means the left hand weight is higher than the right hand child. So, by this sign negative sign, here the 2 is a minus, that is why we can understand the weight at the right hand side is higher as compared to left one. So, we rotate that tree at the right hand side. So, that is called rotate at the left hand side. Again we go by the first sign at the root node, we can understand this is a left rotation, because we have to shift our tree at the left hand side. Now, first L is clear. Now, why we using a second L? If we can cross check the current successor of the unbalancing factor of that node. Here we unbalancing factor node is only a root node, that is a 1. So, that we can cross check the current successor of that node. Here the 2 is the current successor, right successor, and what is the balancing factor of that there is minus 1. Here the sign is minus. Again we know by the sign of minus, the weight of the at the right hand side is higher than as compared to left hand side. So, in a both node, root node and the current successor node having a both are the negative sign, we can go for the all rotation kind of a left rotation. So, by this sign we can understand which kind of rotation we can require. So, by the minus sign we can rotate at the left hand side, by the positive sign we can rotate the tree at the right hand side. Here we having both there as a minus sign, that is why we perform the left rotation. So, left rotation we can by the use of left rotation. So, 1 will become a down at the downside and 2 will become a root node. So, 2 will become a root node, 1 is a left successor of 2 and 3 as it is the right successor of 2. Now, before the rotation part LL rotation 1 is a root node, but after the rotation 2 will become a root node, because 2 is replaced by 2, the position of 1 is replaced by 2 and 1 will be the left child of the root node 2. The last one is 2, in the last ground diagram 2 will become a root node and 1 is a current left successor of 2 and 3 is a current right successor of 2. So, again we calculate the balancing after performing the rotation operation, again we calculate the balancing factor of each and every node. So, 1 and 3 are the leaf node, that is why the balancing factor are 0 0. We can go for the 2 is a root node, again we calculate the balancing factor at the left hand and right hand child. Height of left is 1 and height of right is 1, 1 minus 1 is 0. So, the balancing factor 2 is 0. So, the tree follow the property of AVL tree, by the rotation after the LL rotation the tree is balanced tree. So, this is a way to after performing the rotation part and we can convert an imbalanced tree to the balanced tree. So, this is the first example. Now, go for the next one is a right rotation, or we can call the RR rotation. That both are comes under the single direction rotations. So, in RR rotation every node moves one position to the right from the current position, again to the right from the current positions. To understand RR rotation, let us consider the following insertion operation in AVL tree. Here you can cross check by this diagram, you are inserting 3 elements 1, 2 and 3. So, 3 first to insert 3, obviously tree initially tree is empty, first to when you insert a 3, so the tree is a balance because the balancing factor is a 0. When you insert a 2 is a in the same way when we inserting a new item in a binary tree, in the same way we can insert a new item in a AVL tree. When you inserting a 2 is a when we comparing with 3 2 is less than 3. So, we add at the left successor of the 3. So, 2 is a left successor of 3. Now, the new element is 1. After inserting a 2, again we calculate the balancing factor. So, the balancing factor of 2 is 0 because 2 is leaf node, but the balancing factor of 3 is 1 because at the left hand side only a single child, that is a 2, and the height of at the right hand side only a single child, there is no child, that is why the 0, 1 minus 0 is 1. So, before inserting a 1 in the first diagram, the balancing factor are satisfying, but when we insert a new element 1, because 1 is less than 3 and 1 is also less than 2. So, when we insert at the left successor of, because 1 is less than 2, it should be put at the left child of 2. So, after inserting the new element 1, again we cross check the balancing factor of all the nodes. So, after inserting 1, the balancing factor of 1, because 1 is the leaf node, that is why the balancing factor is 0. Balancing factor of 2 is 1 because height of left is 1, height of right is 0, 1 minus 0 is 1, and the height of 3, balancing factor of 3, the height of the left hand side is 2 generation, that is why height of left is 2, but about the right generation is a 0. So, 2 minus 0, it means the balancing factor of 3 is 2, which is not satisfy the property of AVL tree because the range are not exceed to plus 1. So, the tree is called a imbalanced tree. So, tree is imbalanced. So, we can go for the rotation part. Which kind of rotation we can perform? So, again for the rotation we have to cross check the sign symbol from where tree is imbalanced. So, here we only a single node, that is a root node where tree is imbalanced because it does not satisfy the property, balancing factors does not satisfy the property of AVL tree. So, here we cross check 2 which comes in the positive part. So, positive it means we go for the right rotation. Again we cross check the current left successor which sign is available. Again we cross check the one is again positive. So, we go for the right rotation. So, by the root node the balancing factor is again positive, current left successor again a positive, that is why we go for the right rotation. So, after performing right rotation, so 3 will be replaced by 2 and 1 is replaced by 2 and 3 we take a new as a right child of a 2. So, in the third diagram you can see 2 after the rotation it become a root node, 3 after the right rotation it become a right successor of 2 and 1 as it is a left successor of 2. So, on the third diagram you can cross check the rotation part is complete and the tree after calculating the balancing factor in the third diagram, all the nodes in a leaf node are 1 and 2, balancing factor are 0, 0, satisfy the property of AVL tree and we calculate the root node of 2 the balancing factor. So, that 2 is also as 0 because height of left child is again 1, height of right child is 1, 1 minus 1 is 0. So, after the rotation all the nodes, all the available nodes in that tree are called the follow the property of AVL tree, that is why the tree is balanced tree. So, in this tutorial we cover single rotations parts, left rotation and right rotation. So, I hope you can understand how we can rotate our tree, AVL tree from imbalanced tree to balanced tree, imbalance to imbalance with the help of LL rotation and right rotation. In the next tutorial, we discuss about the double rotation part, that is the LR rotation and RL rotation. That topic, by this rotation we can understand how we calculate, how we imbalance tree to a imbalanced tree. So, in the next tutorial we cover that part. Thank you.